In Part 5 of Lecture 4, we will discuss threads in Solaris. Solaris makes use of 4 separate thread-related concepts. The process, which is the normal Unix process and includes the user's address space, stack, and process control block. User-level threads, which are implemented through a threads library in the address space of a process. These are invisible to the operating system. A user-level thread is a user-created unit of execution within a process. Lightweight processes. A lightweight process can be viewed as a mapping between user-level threads and kernel threads. Each lightweight process supports user-level threads and maps to one kernel thread. Lightweight processes are scheduled by the kernel independently and may execute in parallel on multiprocessors. Kernel threads. These are the fundamental entities that can be scheduled and dispatched to run on one of the system's processors. The figure illustrated on this slide illustrates the relationship among these 4 entities. Note that there is always exactly one kernel thread for each lightweight process. A lightweight process is visible within a process to the application. Thus, lightweight process data structures exist within their respective process address space. At the same time, each lightweight process is bound to a single dispatchable kernel thread, and the data structure for that kernel thread is maintained within the kernel's address space. A process may consist of a single user-level thread bound to a single lightweight process. In this case, there is a single thread of execution corresponding to a traditional Unix process. When concurrency is not required within a single process, an application uses this process structure. If an application requires concurrency, its process contains multiple threads, each bound to a single lightweight process, which in turn are each bound to a single kernel thread. In addition, there are kernel threads that are not associated with lightweight processes. The kernel creates, runs, and destroys these kernel threads to execute specific system functions. The use of kernel threads rather than kernel processes to implement system functions reduces the overhead of switching within the kernel from a process switch to a simpler thread switch. The figure shown here compares, in general terms, the process structure of a traditional Unix system with that of Solaris. On a typical Unix implementation, the process structure includes the process ID, the user IDs, a signal dispatch table, which the kernel uses to decide what to do when sending a signal to a process, file descriptors, which describe the state of files in use by this process, a memory map, which defines the address space for this process, and the processor state structure, which includes the kernel stack for this process. Solaris retains this basic structure, but replaces the processor state block with a list of structures containing one data block for each lightweight process. The lightweight process data structure includes the following elements: a lightweight process identifier, the priority of this lightweight process, and hence the kernel thread that supports it, a signal mask that tells the kernel which signals will be accepted, saved values of user-level registers when the lightweight process is not running. The kernel stack for this lightweight process, which includes system call arguments, results, and error codes for each call level, resource usage and profiling data, pointer to the corresponding kernel thread, and lastly, a pointer to the process structure. The figure shown on this slide shows a simplified view of both thread execution states. These states reflect the execution status of both a kernel thread and the lightweight process bound to it. As mentioned, some kernel threads are not associated with a lightweight process. The same execution diagram applies. The states are as follows. Run. The thread is runnable, that is, the thread is ready to execute. On proc. The thread is executing on a processor. Sleep. The thread is blocked. Stop. The thread is stopped. Zombie. The thread is terminated. Free. Thread resources have been released, and the thread is awaiting removal from the operating system thread data structure. A thread moves on from onProc to run if it is preempted by a higher priority thread or because of time slicing. A thread moves from onProc to sleep if it is blocked and must await an event to return the run state. Blocking occurs if the thread invokes a system call and must wait for the system service to be performed. A thread enters the stop state if its process is stopped. This might be done for debugging purposes. Most operating systems contain two fundamental forms of concurrent activity: processes and interrupts. Processes, or threads, cooperate with each other and manage the use of shared data structures by means of a variety of primitives that enforce mutual exclusion and that synchronize their execution. Mutual exclusion is defined as allowing only one process at a time to execute certain code or access certain data. Interrupts are synchronized by preventing their handling for a certain period of time. Solaris unifies these two concepts into a single model, namely kernel threads, and the mechanisms for scheduling and executing kernel threads. To do this, interrupts are converted to kernel threads. The motivation for converting interrupts to threads is to reduce overhead. Interrupt handlers often manipulate data shared by the rest of the kernel. Therefore, while a kernel routine that accesses such data is executing, interrupts must be blocked, even though most interrupts will not affect that data. Typically, the way this is done is for the routine to set the interrupt priority level higher to block interrupts, and then lower the priority level after access is completed. These operations take time. The problem is magnified on a multiprocessor system. The kernel must protect more objects and may need to block interrupts on all processors. When an interrupt occurs, it is delivered to a particular processor, and the thread that was executing on that processor is pinned. A pinned thread cannot move to another processor, and its context is preserved. It is simply suspended until the interrupt is processed. The processor then begins executing an interrupt thread. There is a pool of deactivated interrupt threads available, so that a new thread creation is not required. The interrupt thread then executes to handle the interrupt. If the handler routine needs access to a data structure that is currently locked in some fashion for use by another executing thread, the interrupt thread must wait for access to that data structure. An interrupt thread can only be preempted by another interrupt thread of a higher priority. Experience with Solaris interrupt threads indicates that this approach provides superior performance to the traditional interrupt handling strategy.